Hey folks, I've got some rolling examples for you. These are just problems we're going to work on and we'll talk about a little bit. So let's say you have a paper towel roll, which is basically a solid disc or solid cylinder, and it's got a mass m and a radius r, and you pull on it with a force F, and it rolls along the table. And that force F is like kind of like you're unwinding it, okay? So given that, I'd like to determine the acceleration of the center of mass, okay? And also, what's the minimum coefficient of static friction to keep the paper towel roll from actually sliding? We want it to roll, not slide, okay? So what do I need? And then also, which way does friction point? Which direction does friction point in, okay? So first of all, if we were in class, I would be doing a demo, and the demo would be, what if I took the paper towel roll and pulled it from the bottom like so, okay? Tried to unwind it from the bottom like that. Which way would it go? All right. So I challenge you at home to try this, okay? The net force is to the right, so it's going to accelerate to the right. Again, don't take my word for it. Try it out. Now, when you do this, make sure you keep the force parallel to the table. Don't pull up on the paper towel roll. Just pull to the right. So keep your hand very low on the table, but the paper towel roll will accelerate right, okay? And it's going to be the same thing for our example we're doing here. The paper towel roll is going to accelerate right. All right, so we first got to draw an FBD. Okay, so we've got F, okay? And we also have the force of gravity, which will act at the center and act down. So that's mg. You have the normal force acting from the bottom through the center up. Okay. And then we got friction. Okay. So you would imagine that friction should go left. So let's guess that. All right. And then we'll see. And if we get a negative value for friction, then we know we got it wrong. Okay. So we'll start with net force equals ma. All right. We'll say to the right's positive. So you got our pulling force minus friction equals ma. Okay, so got a couple unknowns there. We don't know A and we don't know friction. So then we're going to do net torque equals I alpha. Okay, and I'm going to do net torque about the center of mass. So I'm going to look at here. Okay, now the way we've drawn this, there's four forces. Okay, the normal force and mg don't create torque because both those lines of force act through the center of mass, so they don't cause torque. The forces that do cause torque are friction and our pulling force, and they both are trying to make this thing spin clockwise the way I've drawn them, so they're going to add. So torque is R cross F. So we got RF plus R friction equals I, which for a solid disk would be 1/2 mr squared, and then alpha, which is A over R. Okay. Now, thankfully, all the radii cancel out. Each of these cancels with one of those, and then these two cancel. And you get F plus friction equals 1/2 ma. Okay, so I'm going to start by getting rid of friction and solving for A. So if I solve this equation for friction, I get 1/2 ma minus F, and I'm going to plug that in here for friction. So friction minus quantity, 1/2 ma minus force that I'm pulling with equals ma. And I can solve for A now. I'll do a little algebra here. So we got minus a 1/2 ma there. Then we got a plus F equals ma. We've got 2F equals 3/2 ma. And if I solve for A, I get 4F over 3m. Okay, so there's the acceleration of the paper towel roll. Now, at this point, you should be able to answer which way friction points. Okay, if there were no friction and the only force acting on the paper towel roll were F, the acceleration would just be F divided by m. Well, we've got an acceleration bigger than that. So it turns out we guessed wrong on friction. When we plug this back in for A to solve for friction, it turns out we're going to get a negative value for friction. Okay, so I'll show you that. Let's see, we'll do this right here. Okay, so friction, I'll use this equation here, and I'll plug in A. So the force of friction is equal to 1/2 ma, which we wrote as 4F over 3m, and then minus F, which is, now the masses drop out here, and you get 2/3 F minus F. So you get negative 1/3 F. So it turns out that friction actually points to the right and helps our paper towel roll stay in place and not slide. So we guessed wrong on friction, but that's okay. This is the magnitude of it, and now you know it points right. Okay. Now what about the coefficient of friction? Okay. Well, the coefficient of friction has to be at least equal to or greater than. So equal to, or actually, I'll write it this way: force of friction has to be less than or equal to US Fn. So the coefficient of static friction has to be greater than or equal to the force of friction divided by the force normal. Okay. Well, the force of friction, now we just look at magnitude here. So that was 1/3 F, and the force normal is mg. So your answer is F divided by 3mg. So that's the minimum value of this coefficient of static friction to keep the paper towel roll from sliding. Okay. Now, a note on that, it actually depends on how hard you're pulling. So the harder you pull, the more friction you need to keep the paper towel roll from sliding. Okay, and if you think about it, if you try it out, it'll make sense. The harder you pull on the paper towel roll, the more likely it is to skid across the floor. Okay, that's our first example. I've got one more for you. This one will be pretty quick. Let's say that this is not technically rolling, but it's like rolling. Let's say I have a yo-yo, and it is attached to the ceiling. Okay, so a yo-yo is similar to a disc of mass m and radius r. And my two questions are very simple. What's the acceleration of this system downward, and what's the tension in the string? Okay, so like almost all of our other questions, this is going to start with an FBD. So if I draw an FBD, you've got mg down, and you have tension acting upward. Okay, I'm going to say down is positive because I know the yo-yo is going to accelerate down. So if I do net force equals ma, I get mg minus t equals ma. Now, of course, I've got two unknowns. So then I've also got to do net torque equals I alpha. Okay, and I'm going to look at the center of mass again. Okay, so if I look at the center of mass and I look at the forces causing torque about the center of mass, the only force that's making this thing spin in this case is tension. Mg acts through that center, so it's not causing a torque about the center. So torque is R cross F. And by the way, I keep repeating that because a lot of people forget the R there. Okay, so make sure when you're finding torques, you're actually multiplying by R, or a radius of some kind. So we have R times T equals I for a disk about its center is 1/2 mr squared. Okay, and then alpha is equal to A over R. And surprise, surprise, the R's all drop out. Doesn't matter how big or what the radius of this thing is going to have the same acceleration. I get an expression for tension. Tension equals 1/2 ma. Okay, and then to find the acceleration, I can just plug that back into here. So I'll do that over on the left over here. So we got mg minus 1/2 ma equals ma. Hey, look, all the masses drop out, so it doesn't matter what the mass of this thing, and whether it's made of wood or lead, doesn't really matter. And I get g equals 3/2 a, okay, or a equals 2/3 of gravity. So there's our acceleration, and then you can take that and plug it into your tension equation to get your tension. So we get 1/2 m, and then this is 2/3 g. The 2's drop out, and you get tension equals 1/3. Oh, sorry. Tension equals 1/3 of the weight. Okay, so 1/3 of mg. Okay, so that's a pretty simple example of it. And again, technically it's not rolling, but it's very similar to rolling. So I hope those two examples were helpful, and thank you very much.